Now it's time to move on to the another type of feature selection, which is embedded type feature selection. The first one is lasso. But before we get into the lasso, let's have a quick glance of uh, what is basically embedded type feature selection. So embedded type algorithm integrate the feature selection process within the model training process, allowing for simultaneous optimization of both the model and the feature subset. So these algorithms automatically select relevant features as part of the model training, resulting in more efficient and accurate models. So embedded methods are particularly useful when the dataset has a large number of features and traditional wrapper or filter methods may be computationally expensive or prone to overfitting. So by embedding the feature selection within the model, this algorithm can exploit the inherent feature selection capabilities of the learning algorithm itself. So some popular examples of embedded type feature selection algorithms include LASSO, L1 regularization, Ridge, L2 regularization, Elastic Net, and other tree-based algorithms like random forest and gradient boosting. So these algorithms employ regularization techniques or tree-based mechanisms to assign importance or weights to the features during the model training process. So this importance or weight information is then used to rank or select the most relevant features, effectively performing feature selection as an integral part of the model building process. Hence, let's begin with lasso. So what is lasso? So lasso is nothing but least absolute shrinkage and selection operator, and that is lasso. So lasso is an embedded type feature selection method that combines regularization and feature selection. So that's what is lasso. So the lasso technique combines regularization and feature selection. So it's commonly used in machine learning and statistics to select a subset of relevant features and perform variable selection. So lasso is particularly effective when dealing with high dimensional data sets where the number of feature exceeds the number of samples. So let's define the lasso first. So linear lasso is a linear regression method that imposes a penalty on the absolute size of the coefficients, forcing some of them to be exactly zero. So this penalty encourages sparsity in the coefficient vector, effectively selecting a subset of the most important features while shrinking the coefficients of less important features towards zero. So now let's look into the applicability of it. So lasso can be applied to single sample and multi-sample datasets. It's commonly used in scenarios where the number of features is large and there is a need to select a subset of relevant features for prediction or interface of prediction or inference. So mathematical equation of lasso. So the lasso optimization problem uh, can be explained with the following equation, or can be so a lasso can be mathematically modeled as the summation of loss function and regularized term. So that what you see on screen is the mathematical uh, formation of lasso, so or mathematical manifestation of lasso. So now out of that, y sub I is the vector of target values, and we have x here that you see x x sub ij. So x is the matrix of input features, then we have w. You see that here you say w sub j, and here also w sub j. So w is the vector coefficients to be estimated. Then lambda, you see the lambda. So lambda is the regularization parameter, very important. Lambda is the regularization parameter that controls the strength of the penalty term, and this is what the mathematical form of our lasso regression. Let's go into the algorithm, so and how it works. So let's begin with the first step. Initialize the coefficient vector w. So once the w has been initialized, then compute the residual vector r is equals to y minus capital X times w, or so here that you can see on the screen exactly that residual vector, or the residual function. Then update the coefficient vector w by solving the optimization problem using coordinate descent or other optimization algorithms. Then repeat steps 2 to 3 until convergence or a specified number of iterations, and use the final coefficient vector to select the relevant features based on their non-zero coefficients. So that's how our algorithm works. Now let's look into the applications of that. So Lasso has various applications in regression analysis, feature selection, and high dimensionality data analysis, and some of the fields where the Lasso is heavily used. And the first one is gene expression analysis. So gene expression analysis, identifying a subset of genes that are relevant for predicting disease outcomes. Then financial modeling, so selecting important economic indicators for predicting stock prices or market trends. Then we have the most important one, image processing, so extracting the meaningful features from images for classification or object recognition. Then NLP, the most important one, natural language processing, feature selection and text analysis tasks such as sentiment analysis or document classification can also be done through this. And so real life examples where it will be exactly applied with what kind of activity it can do in the respective field. So predicting house prices. So selecting the relevant features like the number of bedrooms, square footage, and location to predict house prices. Then we have the credit risk assessment. So identifying the important factors like income, credit score, and debt to predict the likelihood or of default for loan applications. Uh, and we have the third one, which is a disease diagnosis, selecting the informative biomarkers or clinical features for diagnosing diseases based on the patient data. So overall, Lasso is a powerful technique for feature selection that promotes sparsity in the coefficient vector, allowing for the identification of the most relevant features while discarding irrelevant or redundant ones.